So what you're gonna see is quite typical in mathematics, and that is to work hard for something, and then once we have it, we use it over and over again, and we build on it. For example, we just learned or reviewed that the sum of the inner angles in any triangle is 180 degrees. Now, what about a 4-sided polygon, a 5-sided polygon, 17-sided polygon? What is the sum of its inner angles? This is a 7-sided polygon, but it really shouldn't matter. We're just going to use n, so n is going to be a number of sides. And now we're going to use what we know, which is the sum of the inner angles in triangles. We just throw in a point somewhere inside, and then we're going to connect this point with every outer point or vertex. These points are called vertex or vertices. So we throw in a point, and then we connect every vertex with that point. This is called triangulation. We triangulated this poor thing. This here is a triangle, right? So we know that these three angles add up to 180. We don't know how many are individually, but we know the sum. We also know that this other triangle here has three angles that also add up to 180, right? The three red angles also add up to 180, right? Here is some good news. If this is a 7-sided polygon and you throw in a number, you're going to have 7 triangles, 1 triangle per side. So that's kind of good news. Okay. If we mark up all these angles, and the ones that we colored with the same color, they add up to 180 each. So then, with 7 sides, we're going to have 7 times 180. With n sides, we're going to have n times 180 degrees, right? But this is not good as a final answer because we have some extra stuff. We counted something that is not part of what we're looking for, and that is here. You see this brown angle? This is not an angle in the polygon, it just was created when we triangulated the polygon. So is this, so is this. So this is what we can call the overcount. But visually it shows that, well, that's a full angle, that's 360. So if we just adjust our answer by subtracting the overcount, then we're going to be good. And so in case of a 7-sided polygon, the sum of the inner angles is 7 times 180 minus 360. Well, this is just 2 times 180, and 7 minus 2 is 5. 5 times 180 is 900 equals to 900 degrees. Okay, here this is a perfect formula. So multiply the number of sides by 180 degrees and then subtract 360. This is perfectly fine, and this is the form that I use. But if you remember from algebra, we can factor out 180. What would happen? If you factor out 180, here 180 is getting multiplied by n, and here 180 is getting multiplied by 2. These two are the same, right? If you distribute the 180, you get this. But this also represents another technique, which I don't like as much as I like the one that I showed you, is that we basically pick a point, then we triangulate the poor thing like this. Although there is no overcount, now we have to argue why exactly n minus 2 triangles were created. I think this method that I showed you just avoids that. We can check. Here is a pentagon, so if we pick one point and we triangulate from there, we get 1, 2, 3. So for 5 it works that it's 3. So you can check a few other cases. This is the formula, and I think the best way to remember is to recall this story. You don't even have to draw it. You can just mentally picture it, that you have a, I don't know, 13-sided polygon, you throw in an inner point, you create 13 triangles, that's 13 times 180, and then in the middle there is the overcount, which we subtract. So it's 13 times 180 minus 360. Okay, so then what now? Can we find the inner angle of a polygon? And the answer is, well, it depends. A polygon is regular when every angle and every side is the same. Here is the regular triangle. Here is the regular quadrilateral called a square. Here is the regular pentagon, 5-sided polygon. Here is the regular 6-sided polygon. So on and so on. You see, the more sides we have, the more the closer this picture gets to the circle. So it's good to draw them starting with a circle. So if we know the sum of the inner angles, then we can conclude what an individual angle is, provided that they're all equal, right? So let's say we have a 15-sided polygon. So if we have a 15-sided regular polygon, what about the inner angle? Well, we imagine a 15-sided polygon. We triangulate it, create 15 triangles. Well, that's 15 times 180 degrees, the sum of all those angles. Then we adjust for the overcount, which was created around the point that we artificially threw in. And this is the sum of 15 angles. So if we want to know one angle, provided that they're all equal, then we just divide it by 15, right? And so this is 2340 divided by 15, which is 156 degrees. So now what we learned, and it all goes back to the sum of the angles in a triangle is 180 degrees. We learned how to find the sum of inner angles of any polygon and even the individual angle of regular polygons. Thank you for watching.